A driver moving at 54 kilometers per hour suddenly spots an obstacle exactly 30 meters ahead and slams on the brakes. The tires lock. The car skids. We can determine exactly how this ends by looking at the mechanics of the motion itself. To calculate the outcome, we have to freeze reality and build a mathematical grid over the physical world. First, we need a reference point. The exact moment the tires lock up becomes coordinate 0. The obstacle sits further down the line at precisely plus 30 meters. This establishes the position of every object on a single axis. In physics, the actual path an object takes is its distance, but its displacement is much simpler. It is the net change in position from the starting point to the finish. Because our car is skidding in a perfectly straight line, distance and displacement are identical. This is our first rule for modeling the encounter. We have a fixed starting point and a hard 30-meter limit. Knowing the displacement gap is only half the story. To predict the stop, we have to factor in the time interval of the skid. We also have to distinguish speed from velocity. Speed is just a raw number, but velocity is a vector. It tells us exactly how fast the position is changing and in which direction. When that velocity changes, we measure the rate of that change as average acceleration. Braking is simply an application of negative acceleration. The brakes exert a force in the exact opposite direction of the car's forward velocity, draining that velocity until it hits 0. We see constant acceleration throughout nature. If you drop an object from a height, Earth's gravity pulls it straight down, increasing its velocity by a constant 9.8 meters per second squared. For our driver, the outcome depends on whether the negative acceleration of the brakes can reduce the car's velocity to 0 before the displacement reaches that 30-meter mark. Scientists use graphs to visualize these forces simultaneously, extracting data from the physical world. On a position time graph, the steepness, or the slope, of the line tells us the velocity. As the curve flattens out into a horizontal line, the velocity has dropped to 0, and the object is at rest. We can also use a velocity time graph. Here, the downward slope of the line directly represents the constant negative acceleration of the brakes. This graph provides another metric. Calculating the area locked underneath that sloping line gives us the total displacement of the skid. The geometry of these graphs is distilled into the 3 kinematic equations, which allow us to calculate motion without needing to draw a new graph for every scenario. To solve our crash scenario, we use the third equation. We take our initial velocity, 15 meters per second, and assume the brakes provide a constant negative acceleration of 4 meters per second squared. By squaring the velocity and dividing it by twice that acceleration, we can find the exact distance needed to stop. The calculation results in a stopping distance of 28.1 meters. The car stops with nearly 2 meters to spare. By reducing motion to these specific variables, we can accurately predict a physical outcome before the event is even over. But motion isn't always a straight line. What if the driver didn't use the brakes at all, but instead swerved the steering wheel in a perfect arc? This is uniform circular motion, where an object travels along a circular path at a constant speed. This creates an apparent paradox. If the car's speed never changes, how can it be accelerating? The answer lies in the definition of velocity. Because velocity requires a direction, and a circle is a state of constantly shifting direction, the velocity is always changing. That change in direction is, by definition, acceleration. This means that turning a steering wheel is a form of acceleration, even if you never touch the gas or the brake. These rules extend to the largest scales of the universe. Satellites and planets in orbit follow these exact principles of circular acceleration. The universe is full of complex movement, but by isolating a few variables, time, displacement, velocity, and acceleration, we can map the past and calculate the future of anything in motion.